Welcome everyone to this year's final seminar in the Robotics Today series. Today we're thrilled to welcome Professor Carlotta A from the Rose-Hulman Institute of Technology, where she is faculty at the Department of Electrical and Computer Engineering. Professor Berry has a bachelor's degree in mathematics from Spelman College, a bachelor's degree in electrical engineering from Georgia Tech, a master's in electrical engineering from Wayne State University, and a PhD from Vanderbilt University. She's one of a team of faculty in ECE, ME, and CSSE at Rose-Hulman to create and direct the first multidisciplinary minor in robotics. Her many achievements have been recognized, among others, by being one of the 30 women in robotics you need to know about in 2020. And her research interests are in robotics education, interface design, human-robot interaction, and increasing underrepresented populations in STEM fields. She has a special passion for diversifying the engineering profession by encouraging more women and underrepresented minorities to pursue undergraduate and graduate degrees. She feels that the profession should reflect the world that we live in order to solve the unique problems that we face. We feel the same way, and we are looking forward to Professor Berry's talk on robotics education to robotics research. Take it away, Carlotta.
Thank you so much for having me. I really do appreciate this invitation from Robotics Today. I'm going to now share my slides so we can get started. And so once again, I am a professor of electrical and computer engineering at Rose-Hulman Institute of Technology. If you don't know where it is, it's in Terre Haute, Indiana, which is about an hour west of Indianapolis. It's typically ranked in the top 1 to 2 for undergraduate engineering education. So that's what we're known for. And you're going to notice that that's really what I focus a lot on in my talk today. So first, I want to share a little bit about who I am. So I like to say that I'm an intersectional robotics engineering professor. Ernest Boyer states that the work of the professoriate may be separated into 4 separate yet also overlapping functions. They are the scholarship of discovery, integration, scholarship, application, and teaching. And he proposes that this must be a more inclusive view of scholarship because these 4 dynamically interact to make an interdependent whole. So you can no longer separate these into these silos of today I'm teaching, now I'm doing research, or now I'm doing scholarship. And so what this looks like, especially at a teaching school like where I work, one thing I did not mention is that Rose-Hulman is primarily undergraduate, which means we do not have any PhD students, and we have very few master's students, and most of the ones we do have get course-based masters. So a big part of how we get our research and professional development done is with our undergraduate students. So this knowledge is acquired through research, synthesis, practice, and teaching. So first, if you have the scholarship of discovery, which is this investigative research, this is the type of research that most people traditionally think about that professors and faculty do. And if you think about these like building blocks, that builds on this scholarship of integration, which is making connections across disciplines, which robotics is ideal for. I talk a lot about multidisciplinary robotics because it's a great way to show the connections between the disciplines. We like to tell our students that no one graduates as a mechanical engineer and goes to work in a cubicle with all mechanical engineers. So you need to be able to speak the language of electrical, computer science, software, and you need to know a little bit about what they do as well. Then the next building block is a scholarship of application. How do you take this knowledge you've acquired and apply it to real world consequential problems, also considered service or service learning? And then you bring all of those together in the scholarship of teaching. And this is the purpose of my talk today, to talk about how I use my teaching and robotics to not only diversify the field, but also to recruit students to do professional development and research and show them the application and integration of their work and how it applies to all of these very rich and interesting problems. So the scholarship of teaching is how we educate and entice these future scholars to transform, transmit, and extend their knowledge, and of course, encourage some of them to go on to graduate school study. So what I like to say is because of this intersectional way in which I look at what I do as an academic and a professor, I have created this term that I completely made up called the nowhere STEMinist. So I promote the STEM by bringing robotics and STEM to people and bringing people to robotics and STEM to educate and diversify the profession. I think the most awesome thing about robotics is the fact that people from 9 to 99 still get excited about a robot. So when I tell them that I do robotics work, they want to know all about that. So by sharing that, I'm able to draw more people into the engineering profession. And I also can use those same robotics in order to recruit more students to STEM, and as well as to send my students out to do more of that type of work. So the way that I talk about myself in this intersectional nature is I just call it a nowhere STEMinist. So here's an example of what me being a nowhere STEMinist looks like. So over here on the left, we have a picture from my freshman design class, which I will talk about some more today, where I used a robot to teach engineering design. In the middle, I have some examples of how I use robotics for STEM outreach to recruit more women as well as minoritized populations into STEM. So at the top is the first Lego League and VEX robotics team. It's a Girl Scouts team. It's also my daughter's team. In the middle, I am a first robotics judge, as well as a judge advisor. And I was also the chair of the Crossroads Regional at Rose-Hulman. So that was my Volunteer of the Year award. And at the bottom, I do a lot of robotics workshops for several organizations. So this one at the bottom was at an all-girls college that was doing STEM outreach for young girls. And then also on the right is an example of using robotics to do research beyond the classroom with my students at Rose-Hulman. And so a slide that I share a lot when I'm recruiting young women and minoritized populations into STEM is this one. And I call it Breaking the Mold, hashtag I look like an engineer. And I tell them that we're trying to get to the point that when you go to Google and you Google engineer, this is not what comes up first. And what you would see first is young women and people of all races, etc. So a big part of what I do as the nowhere STEMinist is working to break the mold. And I think that robotics is an ideal mechanism in which to do that. So multidisciplinary robotics is the key to doing this. And I think it's because mobile robotics is inherently multidisciplinary, which means that if someone comes to me and tells me that they're interested in coding, electronics, sensors, biomedical systems, whatever that may be, I can tell them, I think I got a robot for that. I think I have something in robotics that works for that. At Rose-Hulman, we have found that our robotics minor is more frequently pursued by students in computer science, software engineering, electrical, computer, mechanical, and biomedical engineering. However, it is available to all students, but these are the populations that seem the most drawn to it. I talk to them a lot about the benefits of multidisciplinary work and that you are more marketable when you graduate, because even if you don't go to work for a robotics company, because we know those jobs may be few and far between, you are now skilled in controls, automation, kinematics, artificial intelligence, etc., and that works. However, I will say that multidisciplinary robotics does pose some unique challenges, such as the students do have divergent interests, different prerequisites, and different hardware and programming abilities. For example, our mechanical engineering students take MATLAB their freshman year, whereas the EE and CSSE students take Python and C. That means when I have them in my mobile robotics course, they don't all know how to program in the same languages, and they all don't have the same level of understanding of programming. Another challenge we have is mechanical and electrical and computer engineering students take controls. However, computer science and software engineering students do not. I make some assumptions about their ability to do controls in my mobile robotics course. Then, of course, some students want to build a robot, some just want to write software, and some have other interests as well. And so the key in multidisciplinary robotics is, how do I make this enriching and engaging experience for all of those populations who are all in the same class together? So I'm going to share a little bit about that today. So they go through these several classes where we talk about this mechanical system with electronics and software on it. And then we also have multidisciplinary senior design at Rose-Hulman. So if after they finish all of their robotics related classes, they want to continue to collaborate on these multidisciplinary teams, they can enroll, instead of in their department senior design class, they can enroll in the multidisciplinary senior design class. And we typically have clients who have something either robotics or automation related that we can put those students on, because that will be the closest to their real world experience once they graduate. So the robotics minor curriculum at Rose-Hulman has some core classes as well as elective classes. And the key is students must take classes in another department to get their robotics minor. So in other words, a mechanical engineering student should take CS programming, or an electrical engineering student would take mechatronics or kinematics. Computer science student could take controls, or they could take artificial intelligence. All of the students in the robotics minor are required to take robotics course as well as robotics. Those are kind of like the cap courses of our robotics minor. And then we also have a richness of electives in order to satisfy their divergent interests. So we have electives in image processing, computer vision, brain-machine interfaces, neuroprosthetics, wireless sensors, pattern recognition, Android or iOS development, wireless sensors, machine learning, or swarm intelligence. So Rose-Hulman has 3 freshman classes that have robots in them, because we kind of know that's like the hook. We talk about their freshman year. You don't want them just doing calculus and physics, although we know those are important. We want to give them that hook, something to get them excited about being in engineering or being in computer science. So we like to say that we're trying to turn these thinkers into hackers and tinkerers. So the way that we do that is we integrate robotics into the freshman curriculum. In ASEE freshman design, which I teach, that class is about process and critical thinking, teamwork skills, programming, electronics, but they also have to do technical presentations and documentation. Some years ago, we gave our Lego robots, which used to be in this class, to mechanical engineering, because we thought that had more of a mechanical focus. And we changed to an Arduino on top of a parallax robot for ASEE freshman design, so that they could do more electronics to help prepare them for their circuits and their microcontrollers courses. And there's also robotics in CS intro programming courses as well. And that's an in-house robot that they've actually curated specifically for the class. So here's a small snippet of some of the old and new freshman design highlights. This course always culminates with a competition. The competition is not tied to their grade, because we know that's a stressor for students. Their grade is based upon the design process. The competition is for fun and bragging rights at the end of the quarter. So every year there's a different challenge. So they have to build robots to meet some design challenge. And as I said, we originally started with mechanical engineering robots. So this year, the robot had to be teleoperated to make math equations. And their goal was to build the math equation that would yield the highest number. So that's what they're doing. And then there are multipliers based upon whether your math equation was stacked or vertical. We also have done robot soccer. I'm going to move this ahead a little bit. We've also done spelling, where their score was basically kind of like Scrabble. So obviously the longer the word, the more letters. So this is Robot Scrabble, where they play against each other to figure out what words they can build. I think the winning word that year was Jabberwocky, which I believe they're spelling there. We've done robot bowling, where we now had to look at creative ways to bowl, because you obviously have to build a robot to be able to knock over the pins. And we also did robot towers. As you can tell, we like recycling a lot. So we use those same baby blocks for a lot of different things. And then we transitioned to the parallax robots. And so this was the first year we did that, where now they did Arduino microcontrollers, and they then had to design the sensor suite as well as the controls to either do autonomous or remote controlled robots. Obviously you get more points for autonomous, to either pick up eggs and something like that. So here's an example of other projects that they did in order to prepare for the robotics challenges. And this year it was to build a Tetris game using LEDs.
So it remembers when you turned it off?
No, like.
So here's one final video from last year. Welcome to the Monster Mash. And so you get extra credit for dressing up if you were wondering why people are dressed up, because they want those points. Here's another one. I'm going to skip that one for the sake of time. So transitioning between the freshman and senior year, they take those core courses as well as those electives like controls, kinematics, microcontrollers, etc. Then their senior year, they take mobile robotics and robotics engineering. I teach mobile robotics. So this is a highlight of my mobile robotics course, and this is what we cover in that course in a 10-week quarter. We start off with the history of robotics, so we talk about robot hardware, such as end effectors, grippers, etc., things like that. And then we talk about robot sensors, and from there we extend to perception, and we look at reactive control, obstacle avoidance, as well as wall following. And then cognition. How do you recognize things about your world to make decisions? Is it a wall? Is it an obstacle? Should I go to goal? Should I go around it? Things like that. And then we end the course with navigation competencies. So we look at path planning, topological and metric path planning, as well as localization, navigation, and mapping. So I'm going to share a little bit of the videos from this class and then talk about how I transitioned them from this into research. In this course, they are required to do weekly readings on state of the art in robotics. So they have a paper they read every week. And I try to pick one that's obviously not too high level because they are juniors and seniors in undergrad. But I typically try to touch on different topics that they may find interesting. So we might read a paper about human robot interaction by Robin Murphy, or we've read some of Maya Matarik papers as well. And then the students will come to me after class and ask about it. Like, I didn't understand this, or can you explain this to me? And I use those students who seem to show that extra interest to recruit them in order to do robotics research. So I'm going to show a little bit of the videos from this course and then show you some of the work the students have completed beyond that. Oh, I'm sorry, the video cut out. I'll try it again. So the interesting thing about this robot is this was not the robot for the class. This was a student who said they didn't like the robot I had offered for the class. And so he did the entire labs with his own robot, which is why I was taking this video. This happens typically at least once every other quarter where students tell me they don't like my robot. They watch so much CGI and so much television and movies that they always think my robot is not up to the standard and that they could do better. And I try to tell them that my class is about teaching robotics concepts, not giving them the top of the line, state of the art technology. So this is an example of a student who actually called my bluff and said, I can do the entire class with my own robot, and he did. So that's what this video was from. And the interesting thing about this class is it has students from all of those disciplines in it. I will typically encourage them or put them on teams so that there's no two students in the same major together. So that I put a computer science student with an electrical engineering student to make sure that there's somebody on the team who knows controls. Or if I have a mechanical engineering student, I might put them with a software engineering student in order to have someone who knows a little bit more about software development. In this class, I don't teach coding at all. I give them assignments and I tell them your job is to get the robot and the odometry error and the sensor error and all the things you don't like. You have to compensate for that and show me you're able to achieve that. So this is an example of hybrid control where the robot is switching between a reactive control, wall following and docking, and then path planning back to the wall. And so here's the culmination of the class where in an artificial world, the robots either have to plan a path from a start to a goal, or they have to create a map of the world, localize in the world and plan a path from the start to the goal. And so currently in the course, all of these are disjoint activities. My future goals for the course are to have the students do this with SLAM. We're not quite there yet. Sometimes the limitations are based upon the memory, because we're doing this on Arduino microcontrollers. But I've changed the robot as well as the software 4 to 5 times since I've been teaching this class since 2007. In undergrad, I never got to touch the robot. So a big thing with me has always been that when I taught an undergraduate robotics course, the students have to touch the robot. So our challenge is making things rich enough for them to be able to do it, but not so difficult that they want to quit and give up. So now I want to talk a little bit about how I transitioned them into doing independent studies and research with me. So my research area was in human-robot interaction, in particular human-robot interfaces. And the goal of human-robot interaction is to understand, design, and evaluate robotic systems to be used by humans for natural and effective communication between humans and robots. So this last quarter, right before the pandemic struck, actually, I challenged my students to think about how to make a human robot interface for the last part of the class. And this is the first time I'd ever done this. And I gave them some starters because I knew it was going to be difficult. And I showed them how they could do it in processing. I had several of my students come to me and say, I don't want to use processing. I want to do it in MATLAB, Java, and a couple of other languages. And I told them, well, I don't care if you do that, but I don't know how to do that. And I was so impressed with some of the results of what they did. And they always take the little bit I give them and they grow and do so much more. So I want to show you a little bit of that as well. So one thing I share with them is that for my PhD, I created something called a sensory egosphere, which was a way of representing the artificial intelligence of the robot, such as searching, an internal model of the world, problem solving, knowledge representation, planning, and reasoning. So I tell them on their interface, I don't care what you put on it, but it should be able to do all of the things you're going to need in order to implement these AI algorithms on your robot. So here's an example of the one that I had for my PhD that I showed to them, but I know they may not be able to do something of this level depending upon what software they used. So I wanted to show an example of some of the ones that they were able to create. So here's a student who actually made one in MATLAB, and they figured out how to put an Arduino wrapper in MATLAB to make it talk to the robot. So they could input a map name and put in a start position or goal position, plan a path for the robot. So they would show me that they were able to make the interface, execute the information, and then send it wirelessly to their robot, and the robot would actually model that same behavior. Then they were able to show me also that they could input a map in the world, drive the robot, and have the robot localize on the world in 2 to 3 steps. And we talked about 2 different ways of doing world maps as well. They could do occupancy grids, or here's an example of a topological map as well. And now they're showing me that they're able to teleoperate their robot with those keys as well to drive the robot around to try to create a map. So I'll show you one more where it's actually connected to the robot.
Okay, so this is localization. So for the map of the world, we've translated it to our cell numbers. So we are starting in 3, 2, and we're gonna find out where we are once we end in 0, 2. In our sense, this is 11 and 8. What you're gonna see over here as the robot's moving is this is gonna say this is where we think we are. And then once it settles into one location where it knows it is, it's gonna update our GUI with graphics.
Let's start here.
So the robot should localize
So we now
in about 4 steps.
We were in 3 or 11.
Because that'll be the only place in the world that's not identical to where it started. I hope that makes sense. So it should localize right here.
We finish in 0, 2. We are currently right there, and that is where we started.
And so making the GUI was the new part of this assignment, and being able to show me that you were able to communicate with your robot and show that information.
Okay, so this is localization.
And one more. Here is the same group showing me a mapping example.
Hello, Dr. Berry, and welcome to our mapping video. Before me, you see the GUI, which right now has assumed that every single cell is an obstacle. As the robot moves through, it's going to update saying this is not an obstacle, and these are where the robot is seeing walls from the IR readings. So you're going to see the robot turn a lot. It likes to read in this orientation. We have a custom send format that we're looking for, so we kind of need the robot in that position. So you're going to see the robot move a lot just to line up like this in each cell so these values are correct. Garrett, would you like to explain the robot and how
Basically, we are starting in the bottom left corner or 3-0 in your standings, 3 in our standings. So basically, the robot's going to move through autonomously and getting the correct orientation, like Kayla was saying, and then.
So here's the robot moving through the world. They had choices. They could either do this autonomously or they can drive the robot. It's their choice. So ways they could do it autonomously is you follow center, create a Voronoi diagram, or have the robot always turn right. And it would eventually finish the world. Obviously, you get more points
set it up as live.
autonomously
Plus,
versus
we have a
remote
whole new
control.
world because we're showing you a whole new world.
So once the robot finishes, it wirelessly transmits the map it has created
So before
back
we
to the
look at the
laptop,
final
and it
GUI,
updates on their
we're going to be
interface.
looking for 2 full obstacles and then a wall in between, and we'll also be picking up the IR readings from all the side walls. And so that is what we can see here. 5 and 9 and 7 and 11 are full obstacles. You can kind of trace the outside and see these red blocks represent that the wall is detected. We can also see the inner wall is represented with the IR readings here. Hello, Dr. Bailey.
So robotics engineering is taught by my colleague, and they take this to quarter after mobile robotics, and it's typically in the spring, so they're outdoors. And in robotics engineering, they use GPS as well as Android and iOS to do ball tracking. So they built their robots to go and look for things on the field to collect. And in this case, they either are going to knock off golf balls if they can use their GPS to get there, or collect things and bring them back. So it's also a competition. So they get more points by getting there, and getting the ball, bringing it back, etc. And this is the robotics engineering course. So I've also taught human-robot interaction to non-technical majors. And this was when I was on sabbatical. So this was to students in media arts and science and other majors. And so we used the Arduino robot because we know their technical skills as well as programming skills were not quite as high level, but it's like a survey course on things related to HRI. So this is an example of them using line following and search and rescue robotics to rescue Mario and Luigi instead of running them over. And they also made an entertainment robot to play music. So once again, I would give them the challenge, and their job was to figure out something to make the robot, for example, using it to do entertainment, like for a child, to play music or dance or sing. And they also learned about teleoperation as well as obstacle avoidance and how to interact with their robot for design challenges. So transitioning to research. So now after they get this foundation in robotics through these key courses like programming, controls, kinematics, mechatronics, image recognition, and computer vision, we can then use the competencies they get from mobile robotics, robotics engineering, and human robot interaction in order to do research with me. One of the challenges in doing research with undergraduates is they don't have the prerequisite skills. So it does take a little bit longer in order to get them up to speed. It may take more quarters. And it's really important to get them to document their work well, because it sometimes may take me 2 or 3 years of different students in order to get a product that's publishable or something like that. So that's actually the biggest challenge, is getting them to properly comment and code their work. So here's an example. And a lot of times I'll take whatever their interests are and build my work on that. So this is an example of some students who came to me and said they wanted to make robots that could solve mazes like they had seen in a YouTube video. And so we talked about how to do that with line following. And so they had to show me that they could make the robot follow different types of shapes first. And then the robot had to make decisions at junctures in order to be able to stop and solve the maze. So they built up to the point of being able to do this. And then once they were able to show it in levels, they were able to show me that the robot can make decisions about if it's at the end or how to keep going to know when it gets to the other side. So then I had another student who used the Danny robot, which is programmed in LabVIEW, to do an example of a search and rescue mission. And he designed it. I told him that after you learn the concepts, you design your own search and rescue mission. So his was to rescue Yoda. So here is his robot searching the world to rescue Yoda. I'm going to forward this to a little bit to where he finds Yoda. So Yoda's back in the corner. It's a little hard to see, but once he finds it, he's going to go to his interface to show me he was able to find him.
And it found the Yoda.
And so at that point, the robot would then pick up Yoda and take Yoda back to the exit to rescue him.
And then you would continue. You can see here in the lower right-hand corner, the magnet, and then turn left.
And so here's a student who used the Pioneer robot to because his mission was going to be to make a heterogeneous team that involved the Pioneer robot as well as the Danny robot. I'll only show a little bit of his, but so he had to first show me he was able to program this robot to create these behaviors. Well, the robot is actually operating autonomously, but
Now, did you ever take data down here? So do you know your algorithm actually handles like a hallway like this?
he's passing on the speech pad to make sure
To
he
see
doesn't
like the
crash into
distances in the side?
I did.
He's running
and
his
I would
obstacle
actually- I
avoidance
just moved him
routine,
along,
and he's going to take it out in the hallway and show me that the robot is able to move during the change of classes and
That's
in the
not bad.
hallways and not run into people, so that eventually, when he puts it with one of the other robots, each of them can capitalize on whatever
Sorry,
error,
Cliff.
like just when
Like me,
has a
I'm
camera,
a mess on
have
steroids.
something
He's
else,
doing okay.
and they can work together to achieve some tasks. Sorry, there's a lot of talking on this.
We're trying to get him to the, is that the max? Have you discovered, is it 5,000?
It is 5,000.
Okay.
5,000.
So my student this summer, who took my mobile robotics course, he wanted to study swarming. I actually had never done any swarming before. And so what I told him is that if you can show me a proof of concept of swarming on the mobile robotics robots, then we would get him some robots for him to use virtually in order for him to study swarming robotics. So this video is an example of him showing me that he could do some of the rudimentary work on the mobile robotics robot and then extend that work in order to study swarming virtually. So first he showed me that he could use go to goal in order to send a robot to a location and then wirelessly transmit that information to a second robot so that they could rendezvous and meet at that point. So that's what he's showing here. his next task was to be able to show me that the robots could pursue each other. So if the first robot transmit its location and distance and turning to the second, that it could track it. So it's not necessarily following based upon IR data, but just by sending goal-to-goal increments. We've also done robot following labs in class as well, though, where similar to wall following, they try to maintain a distance based upon IR or sonar data. But this one is purely based upon the first robot transmitting its information to the second one. So over the summer, we acquired some Elisa 3 and some EPUC robots so that he could now use heterogeneous teams of robots and show me that he could do some pursuit as well as grouping algorithms. And this is what he's currently working on, is getting them to work amongst themselves. And then eventually he's going to put the two different types of robots together because they have different sensors on them, make sure that they're able to be combined together. So the last thing I wanted to share with you is the work of a couple of my grad students. So being that we're a primarily undergraduate institution, we don't really have research labs. So my labs are typically our office or whatever corner of the room you can shove a robot into. So when they want to do research, they have to use whatever we can find. So here's an example of a thesis project that a student did. They took a senior design project from the year before that never flew, and he was designing the controller for this quadcopter. This is an example of where you learn from your successes as well as your failures. So he was designing this controller to be able to hover. And unfortunately, this was the closest he could ever get, but he learned from that success, like I said, as well as his failure. So that's what we're showing here. It's the quadcopter. So this was a quadcopter that didn't do anything after it was built for a senior design project. So the fact that he was able to get it to even move on any level at all was an accomplishment. And here's another one of my master's students who took my mobile robotics course, and he felt like that it was cumbersome having to be pigeonholed into one language or one platform. So he designed a modular educational robotics platform that could be programmed with a cell phone, on an iPad, on a computer, in Java, in C, in Linux, in whatever language you want. It could be programmed on the cloud. And he made it out of old robot parts. He made it out of my robot graveyard from all of my robots from prior years. And so his thesis was showing that it was possible to build a robot from the ground up and have it to have the flexibility so that no matter whether a student was ME, CS, ECE, etc., they could program it in whatever language they want using whatever interface they want. So he showed me that it worked for all of the labs. And here's just an example of him showing it working for obstacle avoidance. Okay, I'm not sure what's going on with this video. We may have to skip. There it goes.
Hey everyone, this project is use the robot to do the obstacle avoidance project. The first one, the robot will go, and when it detects something, it will stop. The second one, when it detects something, it will go and try to avoid it. The third part of this project is try to go past like the obstacles. So when the robot detects the obstacles, it will try to make a turn.
So in conclusion, robotics is a great tool, not only for teaching the intersections between these multiple disciplines, but also for recruiting and retaining diverse populations into STEM and getting more people excited about STEM. It's a great way to educate and entice future scholars to transmit, transform, and extend knowledge, and to get them interested into going to graduate school. One thing we are proud of at Rose-Hulman is that our students from the robotics minor have gone on to schools like Stanford, Georgia Tech, MIT, Carnegie Mellon, WPUI. And when they come back to see us at homecoming, they tell us that despite us not having a traditional research lab or a very strong research presence, they are able to thrive in those research environments from the preparation that we give them through these experiences. And so I've shown here that undergraduate and graduate students can conduct robotics research by building this foundation through this essential robot competencies over these 4 years. And that it's essential for somebody to be able to reap the benefits of undergraduate research. So that concludes my talk, and I want to thank everyone for listening and letting me share a little bit about what excites me about robotics. I have here a couple of ways for you to contact me if you have questions other than asking now. My email address, my website, as well as you can follow me on Twitter. I always have Twitter follows. I do put robotics fun facts and engineering fun facts on Twitter rather frequently. And at the bottom, I have a YouTube channel, and Rose-Hulman has a YouTube channel with a lot of my robotics as well as freshman design content. So here are the hyperlinks for that. And with that, I'll stop sharing.
Thank you, Carlotta, for an amazing talk.
Thank you.
My name is Professor Monroe Kennedy. I'm an assistant professor at Stanford in the Mechanical Engineering Department. And it's my pleasure to announce our panel for today. So we have our Robotics Today series organizers, which include myself, Professor Jeanette Bogg, Professor Luca Carlone, and Professor Marco Pavone. We have some fantastic student panelists joining us today. Please forgive me if I mess up your name at all. Rebecca Jang, Michelle Lee, Shreyas Kosik, and Ramya Bamadipati. And we have two amazing guest panelists as well. Professor Sherry Shepard, who's a professor of mechanical engineering at Stanford University. She directs the Design Education Lab, which investigates a broad range of engineering education topics, from the persistence of students and alumni in engineering fields to impact of exposure to entrepreneurship on engineering students' career interests. And we also have with us, joining us today, Professor Maja Marik. Maja is Chan Soon Xiong Distinguished Professor of Computer Science, Neuroscience, and Pediatrics at the University of Southern California. And she's the founding director of the USC Robotics and Autonomous Systems Center and co-director of the USC Robotics Research Lab. And her Interaction Lab's research into socially assistive robotics is aimed at endowing robots with the ability to help people reach their potential through individual assistance and team cooperation. So with that, I'd like to hand this off to our guest panelists. Maja, would you like to start us off with your questions?
Hi, everyone. It's great to be a part of this. And it was so great to see Carlotta's talk, because it just reminded me of teaching undergrads. I haven't taught them in a little while, and I really miss it. And it's just fantastic to see in action what we really like to say about academia, but it's really true, which is that you catch students when they're young and you inspire them, and they go on to do amazing things. And it's really true, and this really matters. And so I loved everything that I've seen. But since it's my job as a panelist to ask something or suggest something, I do have a thought. I think what Carlotta showed us was this, absolute best practice of engaging students in hands-on projects that are challenging, that bring a lot of different expertise together, that are collaborative. It's all the good stuff. So what can we do even more and better? Because this is what we have to keep striving, right? It's never the end. And here's what I would suggest that we think about. When I was teaching these kinds of classes, we were worried about recruiting more students into robotics. Well, I think we don't have to worry about that now. If anything, it's like, oh, wait a minute. So that's fantastic. It's great to be there. But we do, I think, have three really key goals that we should be thinking about. And so I just want to throw those out, get us to think about. This is not really just for Carlotta, it's for everybody. So we obviously have to work much, much, much harder on diversity. That is hardly anything that we have been doing well in general, as a society. And so I think it's a really interesting question of how we structure the challenges of these classes to appeal to a much broader sort of cross-section of students. And as a second challenge, and I'll loop it all together in the third, because what I'm saying, this first bit is obvious. What's less obvious is what exactly we do. So the second bit is you see numerous students wanting to do these kinds of classes, but I think we can all agree that many of them are more interested in learning the tools and using the tools than sometimes problem solving. And what we want instead is we want to teach generations of amazingly talented humans to solve whatever problems are thrown at them, like a pandemic, as opposed to just saying, memorize this list of tools so that you figure out what tools you can pull up, because that's not really thinking. And sometimes they come in thinking that that's what they're learning, and they may tend to really just learn that. And then as my last part, which I think brings it together, I would love to challenge us all of us who are teaching, to have students solve small versions of full stack, real world, compelling problems. So as much as I love seeing stuff about Yoda, because who doesn't love Baby Yoda? I mean, come on, that is a good one. But I really would love it to be a homeless person, or delivering food to, like, I don't know, a third world country, or providing power to someone who's been cut off due to an emergency. So I would love to see what difference it would make, for example, on student diversity, if we posed questions and challenges that they could relate to. And so, for example, I do a lot of work in health, and I have met a much more diverse set of students over the last 15 years since I've gotten into health than I did before. So it's good to do basic research, but especially for teaching, I would love to push us on real world problems, which of course are super hard, right? It's hard enough just to get them to do SLAM in a nice clean room. But if we're going to simulate something, I would challenge us to simulate these real world problems that people hear about and wonder how they can contribute. So here we are in a really difficult year. And the thing that makes, I think, better people and better researchers, and ultimately better society, is thinking about those problems and believing that you can make a difference. And that really starts in those early classes. So what do you think?
So thank you so much. I know it's not just for me, but I'm going to go first. So I absolutely 100% agree with you. One thing that has been on my bucket list, I just got full last year, is to make an advanced mobile robotics course. And exactly what you're saying, put it in there. One of the challenges I had when I first started was I got a lot of people who wanted to play with the robot, but didn't really care so much about the theory. I had to figure out the way to make the course appropriately rigorous, to kind of weed out, I'm just here to play with a robot people, or if you are just here to play with a robot, you're going to be tested or you're going to drop the class. But so that is one thing I've honestly been thinking about, is how to make this course a prerequisite for that more advanced course for people who can do those rich problems that are related to real world things. Because one of the challenges we've been hearing a lot is that a lot of women are not so into electrical engineering, but more into civil and biomedical for that same reason, because I feel like if I'm that kind of engineer, I can benefit the world or I can help people. We know all engineers and computer scientists do that. So by showing them more of that in class, I think we're more likely to do that. So thank you for that. That's definitely on my list, to make a course that follows this one, where we do build on those real world things. Another one I've thought about is having them look at these papers they're reading on the state of the art. How could you build on that in a class assignment, right? Because there's people already doing real world research on these interesting topics. How can you take that into the classroom and build from it?
Wonderful. Thank you. And if you figure out any best practices in that area, I think it would be wonderful to share, because I think there are probably people who are motivated, but it's hard, right? And so then they get blocked because they need to do something quickly. And, we have to grab the hard problem. So thank you. I think it's someone else now, right? I'm trying to not hoard the conversation.
Yeah, Ramya, do you want to go next?
Yeah. Thank you so much for the talk. This was an amazing talk, and it's really exciting to see how the curriculum is being shaped in such an amazing way for future roboticists and researchers. So one of the questions I had was, what are your thoughts about the recent advances in simulation tools and the effective ways of incorporating them in the robotics research and education? And has the recent pandemic kind of made you rethink some of the curriculum changes and shift towards this virtual platform while still engaging all the students equally?
So I actually, answering that question also is answering the other half of what Dr. Matarik actually answered. So I also have taught virtually. I teach mobile robotics in a flipped classroom, and I actually started doing that before the pandemic because the demand was so high, and I'm the only one that teaches this class at my school. Like when I go on sabbatical, the class is not taught anymore. So by flipping the class, I was able to get more students in it. And now when I show up, it's just to do demos and lab work. And I have a whole YouTube channel with my robotics videos and things that they watch, so that the time in class is really about doing technical stuff. You need to do the reading, the lectures, and all of that away from me. But I've done robotics virtually with high school students. And the way that I do that is you don't have a textbook. So their task is to buy the Arduino starter kit. And the current Arduino starter kit actually is microcontroller projects that ends with them building a very, very cheaply constructed robot. So that whole kit is like about $80. So one thing you can do, thinking about what Dr. Matarik said, is the simulator is hopefully an option for children who are not going to have those kind of resources. That's another way we diversify more, is thinking about socioeconomic circumstances. And I think simulators are the key to that. I think it would be awesome to get robots in their hands as well. One thing we've done at my school for our classes, even beyond robotics, is, and I know everyone can't do this, but I'm at a teaching school, is they ship kits to the students and then they give them a self-addressed box, and at the end they ship them back. And I actually recently on Twitter connected with someone who's doing virtual workshops for K through 12 kids similarly, where they do the simulator online, they ship them the robots, they do the same thing on the simulator they did with the robot, and then they ship the robots back. So there are some ways around it. I personally don't use simulators in my class. I always think flashback to undergrad, where I never got to touch a robot and did everything in simulation. And the richness of having students scream and yell from odometry error and sensor error and battery power going out, there's nothing like that. And you don't get that in a simulator. And the other thing you don't get with your CSSE students is they always want to code to the nth degree, and the microcontroller only has so much memory. And so you now have to restrict them, like, oh, you're gonna have to rein that in because that's not gonna download to the robot, you're gonna run out of memory. So there's just some things you can get from a real world experience that you can't get with a simulator, but I think a simulator is a great way to connect with more audiences, especially those who just financially can't afford to purchase a robot kit.
I wanted to ask a follow-up question about online learning. Obviously, with the COVID-19 pandemic, a lot of our teaching has shifted from in-person lectures to online or Zoom lectures. And there are a lot of challenges to moving our curriculum from teaching in the real world, maybe on a blackboard, writing equations, down to on Zoom, where there are a lot of sources of distraction, where students might not be paying attention. What are some best practices that you've seen when you shifted your curriculum to online teaching or a flipped classroom? What are things that you've seen that people should avoid doing that we as educators can do better?
Okay, I know a big one, and this one comes up a lot on social media, and this is beyond robotics. Don't require people to turn their camera on. That is just like no 101. You don't know what people have going on with their bandwidth. So this is K through 12. My husband is in K through 12 as well. So you don't require people to turn their camera on. Let people be comfortable in their jammies, going to school however they want. But more than things that are no-nos, I want to talk about some of the things that I did that went over really well. So one thing I did was I had quiz contests. So good quiz points for the best virtual background if you want to turn your camera on, or best profile. So everybody turn your camera off, but best profile picture. So the people that won made their picture into Bart Simpson or whatever. And then another thing I did that had absolutely nothing to do with the class is we had class sing-alongs, and we have class sing-along week. We did 90s boy bands. So every day for the first 5 minutes of class, we would go to a YouTube video, and for 5 minutes we would rock out to NSYNC or Backstreet Boys or whatever, and then we'd go talk about controls. And the first couple of weeks, I didn't think anybody was singing with me. And then one week, the student was like, Yeah, me and my sister been jamming the whole time. And then one student was like, came in playing his acoustic guitar while I was singing. And so even though it was awkward and we were online and nobody was excited about being there, by me doing those extra things, they were like, okay, she's actually way more human than I would have ever gotten if we were in a face-to-face classroom. So that then made them more comfortable to engage with me virtually on that platform.
Sherry, want to go next?
Yes, Carlotta, thank you for your talk. It was inspiring, and I too enjoy Ernie Boyer's work in framing of scholarship. And Monroe shared 4 of your papers with me that I thoroughly enjoyed eating up. So a question about the K through 12 world, which you've thought a lot about. And I see that you've also had experience, hands-on experience with FIRST Robotics. And I don't know if the demographics of FIRST Robotics has changed, but for a lot of years, it's been dominated by young men and not girls. And I don't know if you see that changing or what the answer is. So part of it is about FIRST Robotics and it's being an entree to thinking about being engineers. And then your work also has talked about, extracurricular versus it being part of the curriculum. So I'm curious what your thinking is about the science and engineering frameworks that some states are starting to adopt. And do you see that actually being built out, for instance, in Indiana or other states?
Okay, so first, I want to apologize if there's anybody from FIRST on the line. I worked with FIRST from 2007 to 2018. And Sherry, thank you. Similar to you, I saw the same challenge. Although I saw them making some traction with women, maybe not to the national average of 20%, I didn't see much going on with minoritized, marginalized populations. And I'm going to be honest, I think it's the cost. I think the price point for participating in FIRST Robotics is huge. It's like $5,000 or more a year to build the robot and to pay to go to the competitions. And if you go to state or to the championship, it's even more. And that's honestly why my daughter's team transitioned from FIRST Lego League, although not as expensive, to VEX Robotics. So yes, the mayor of Indianapolis recently started an initiative where any K through 12 kids who want to do robotics, they can start a VEX Robotics team on a grant. So I've done that with the Girl Scouts for my daughter, and as well as most elementary schools in Indiana. It's called Tech Point Foundation for Youth in Indianapolis. And the Robotics Education Center, they have an initiative. So Indiana is growing. I can't remember what the number is, but the number, even in FIRST Lego League and VEX Robotics, has exploded because of that. So because of that, I've transitioned away from FIRST a little. I still think it's a great program, but I just think financially, as far as diversity, some of these other programs like BotBall and VEX that don't have such a huge overhead financially are going to work better. FIRST works best, I think, if they have corporate sponsors or somebody who can make that kind of money, because asking a high school teacher to have kids go and sell something to make $5,000 a year is a lot. We know most school systems just don't have that kind of money. So that's kind of where I am in that. And I think Project Lead the Way, organizations like that in high school are really important for recruiting more diverse populations. I've talked to some high school kids from that. Another thing we're trying to do at Rose-Hulman is start a speakers bureau, where you recruit faculty as well as engineers, alumni to go into these diverse communities, into their high schools, and let them see a real world engineer and what they can do with their degree. The teachers are hungry for that. Calculus, the PLTW teachers, just to have somebody to come in there and tell them, this is where you're gonna use this when you graduate. So I think that's a great way to connect with them, even beyond robotics. It's just sending these people back into the classroom to talk to them.
Carlotta, I'm also wondering with FIRST, something I've puzzled on is in some ways the competitive nature of it, and that the tasks aren't necessarily, and this gets to a little bit of what Maya was talking about, what are they in service of? That maybe doing something more community-based with the robot or the system that you're designing. Have you any thoughts about that?
I think that's also another challenge. I've had many first alumni in my classes, and it's interesting because although FIRST has this rich history, I don't want to tell too many secrets because I was a judge advisor, so I know some of the underbelly of FIRST. The students are not required to build the robot. FIRST is for inspiration and recognition of science and technology. So as long as the student is in the room, that is perfectly fine for FIRST. So what I have found is I've had students in class who are in FIRST all through high school, but still don't know how to code or still don't know how to do autonomous because they may have been the person on the team who made the brochure for the judges, or their mentor actually designed the gearbox or what. So I agree with you that having real world technology that applies to a real world problem is a benefit, but also I think students being able to get into something where they get their elbows dirty and they get their hair messy and they do the soldering and they do all of that is also equally as important. Competition, I noticed somebody had a question about that. We've heard that sometimes female students are really turned off about competitions. We're not really into the competitive nature of, battling people against each other and seeing who can win. I think it's really about how you frame those problems. So like in my freshman design course, I model good behaviors for interacting with women and men on teams when I teach them. I'm the only Black woman faculty member on my campus. So when I teach my freshmen, I tell them the proper way to address me, and that if you have women on your team, they are going to alternate the leader roles. They are not going to be the secretary. They're not going to take the notes. They're not going to type the papers. So when I come by your group, if I don't see her also doing circuit building, I'm going to call you out on that. And I think by also talking to them about the correct way to do a competition, and we're not going to have that chest beating and yelling and you know what I mean? And that, if we're going to dress in costumes, they're going to be appropriate. We're not going to have people with no shirts on with letters written on their chest. I talk to them about those kind of things and what is not appropriate. And I also show videos in my class. So I'll show the video of the young lady doing AI research where she has to put on the white mask to recognize her face. Or I'll talk to them about, the crash test dummies and how when they first created those, nobody thought about making one for a child size or for a pregnant woman. So in my class, I don't just talk about robotics or engineering, but I bring up some of these topics to make them feel more comfortable with the competition as well as interacting with diverse populations and what you do as a professional so that when they graduate, you don't go work somewhere and do these boneheaded things that get you sent to HR because you've been taught about them in college.
Thank you so much for your talk. I really liked how you talked about how some of your students will kind of independently take a spin on a project you've given them, or they'll implement their own ideas outside of class. I'm curious, do these students ever end up influencing the curriculum for the next year?
Oh, 100%. I'm embarrassed. I'll tell you guys because you're not my students, but sometimes the students have done something and I'm like, ooh, I never thought about that, or like when I first changed robots, a lot of times, we're in constant prep mode. So I will prep just in time. So I do just enough to get to the next class. And so when they're doing the lab, I'll have a student say something to me like, why are you not using the such and such timer on the Arduino? And in my mind, I'm going, there's another timer on the Arduino. So absolutely. So once they do that stuff, the next quarter, it becomes part of the lab. It's required. In fact, the processing HRI lab that I showed where they all had to make the interface, I got that from a high school student. He was doing a project and he made a GUI in processing. And I said, tell me more about this processing. And then after he showed it to me, the next quarter, I made it into the HRI assignment for my students at Rose-Hulman.
Prof. Berry, thanks for this really cool talk. At least very inspirational too. And I think we have a question that's right along those lines. So recruitment is quite different from coding or math in that it's not something we can practice every day. Like we can't increase diversity every day in the same way. Right. But maybe I'm wrong. So are there things that the average student or professor can do on a daily basis to make a positive impact in diversity, equity, and inclusion in engineering?
Well, some things that I do at my school is we started a program called Rose Undergraduate, Building Undergraduate Diversity, or Rosebud, play on the word rose. And so this program also has nothing to do with robotics, but it's about peer mentoring, faculty mentoring, as well as community building. A big part of, we hear why women and minoritized students leave engineering is they feel like they don't have a sense of belonging. They don't see themselves in those spaces. And I talk to my colleagues, because I obviously work with majority white males, and I tell them it's not the responsibility of women and the minority faculty to do the DEI work in the department. Therefore, if I help create this program, it's everyone's job to learn how to mentor these students, to make them feel supported. Me being at a teaching school, it may not be as big of a challenge because we're assuming faculty are there because they want to teach and connect with students. But things you can do every day is be visible and be present. And ways of doing that is when you come to my office and treat me like a vending machine because you want the answer to number 4, I will let you insert your quarter and give you the answer to number 4. But then I'm going to ask, so how are you doing? How's your roommate? How are you getting acclimated? Are you homesick? You talk to them about things beyond, you know, do I do KCL or KVL to solve this circuit? So all of those things work for all students actually, but they have this extra effect of making women, as well as those who may feel marginalized or isolated, feel a little bit more welcome. So these are things I think everyone can do, and that's part of your everyday job. You don't have to start a whole program like I did. You don't have to go to FIRST or Girl Scouts and all this stuff like I do, but just what do you do to touch people where they are each and every day? That was the most lonely part of me in undergrad, is feeling like when I went to go see my professors, they did not want me there and wanted me to leave as quickly as possible and never to return. So if we can even do those small things, I think it makes them feel this is a place for me. They want to see me succeed. They want to see me graduate.
Hey, hey, Carlotta. Also, thank you a lot for your question. I maybe have one question to ask. So one thing I noticed, or one thing I think is also kind of embedded in robotics, is like a constant failure, especially when it comes to hardware. You already mentioned like, oh, in a simulator, there's not the battery that runs out or the motor that breaks, or and so I'm wondering, do you see failure to have a particular role in your teaching, especially when you work with these complex robotics platforms that require so many different skills?
I do. I like to say that failure builds character. And you don't learn how to be a problem solver when everything is perfect. And this senior year is about the time you need to make that transition. If you think about freshman to junior year, most of your assignments are well framed, beginning to end. The professor already knows the answer. They're just giving you little hints and baby steps to get you there. Senior year, you're about to be a practicing engineer. Your boss is not going to give you things they know the answer to. They're not going to give you hints. So senior year is where you need to start experiencing failure with some open-ended questions. That's why I intentionally give them hard stuff that I don't always know the answer to. Luckily, I've never given them anything that they weren't able to solve, even if I hadn't solved it. But they got to learn how to think critically and how to problem solve. Not to mention, they're also in capstone design with an external client at this point. That person is a professional. You can't say, hey, I'm a student, this is too hard. So I do, and I don't want you to think I'm bashing simulators. I just think there's some real richness that comes from failing early, failing often, and learning from your mistake that you will never make again, right? If you spent 15 hours figuring out why that semicolon wasn't where it was supposed to be, you will always check your semicolons in your code from now on. So I just think there's some real benefit to being able to fail and see that. And like I said, I've changed the robot 5 times chasing students who are like, this robot's terrible. This robot sucks. It doesn't work like such and such. It doesn't work like, until finally I said, I don't care. I'm not changing my robot anymore. Your job is to take this ill, doesn't work well thing and make it do what I'm asking you to do. And the biggest part of that is they watched a lot of really cool movies with robots in them and wanted to know why they couldn't make my robot in my class do like what they saw in the movie I, Robot. I tell them your job in my class is to take your robot from a newborn baby to a 3-year-old who can walk from point A to point B. Whatever's happening in that movie, that's something else. But that's what we're doing in this class. I'm not changing platforms anymore to try to make students happy.
Hey Carlotta, I have a question on my side. First of all, great talk. I loved it. And I'm going to ask actually a selfish question because I'm teaching an undergrad course, like, in robotics. And I wanted to hear your thoughts about, a couple of aspects. The first one is about team working and like, what is the role of working in teams for the students? How important is to work in teams to make sure that the students can engage and can enjoy that kind of experience? And also, I guess a more specific question is, what do you think is the size of a team, like, for a number of students in the team that works particularly well? Because what I saw is that if you start having like, too large of a team of students, the experience is that few students will do the job and the other will watch them. So, and the second question is about if you can say something more about the type of assignments that you have in your mobile robotics class. Because I see that you have these video abstracts. I was wondering if the students are also giving presentations, writing reports, like, if there is anything else.
Absolutely. So my freshman class, I think the team size is dictated by the assignments. Freshmen, the class has no prerequisites. It's their first quarter in college. Some of them did Project Lead the Way. Some of them did FIRST. Some of them have done Arduino. Some did Digital Logic. Some have done nothing. So we make the teams 3 to 4 on purpose, because we also use CATME, and CATME is CATME.org. And it's a questionnaire that you can go through where you talk about your skills as far as coding and electronics. We form the teams in the freshman year to make sure we have somebody that knows a little electronics or somebody that knows a little coding. And I do a whole lecture on teamwork where we talk about forming, storming, norming, cooperative teamwork. I talk about the assignments, how they have to rotate every other week, who's the leader, who's the hardware person, and who's the software person. So I'm very clear in their freshman year about how to make sure the team is functioning well. They have to give me progress memos and reports only on how the team is working, as well as how they're working on their project. So freshman year, we really micromanage the teams to make them go well. And despite that, I've still had some dysfunctions. But they're freshmen, they're coming out of high school. They don't know how to work well on a team. I have to teach them. And so senior year, students are more adamant about being able to self-select their buddies, because they now know who's a slacker and who's a hard worker and all that. So the only requirement for my seniors is 2 per group in mobile robotics, because everybody needs to be doing something. And what I've seen is they normally alternate by the week, one person writing the code, the other writing the memo. Every week they have to write a lab memo. Every week they have to turn in properly commented code, and I teach them what properly commented code means. It has to have a header, it has to have block comments, it has to have appropriate inline comments, no magic numbers, global and local variables, and it has to have functions that are appropriately named. Because in the past, I've had students name their functions curse words when they got mad at me. So a function name is wall following. A function name is not Dr. Berry sucks. So they have to have appropriately named variable and function names. And they are graded on how well their code is organized and works. They're graded on the demo, and they're graded on the lab memo. They have to write a full technical report on a project. The navigation one is a full technical report in IEEE format, just to get the practice. So it has to have a literature review. It has to have references and citations. It has to have method, results, conclusions, just like the same stuff I would do in a paper that I was presenting at a conference. And that's for the final paper. They do oral reports in the freshman class, but we don't do oral reports in the senior class. And I think I've answered most of your questions. They also do online quizzes every week for either the textbook reading, and I did write a book for the class. I used to use Maya's book for the class, actually. I didn't tell her that. I'm standing a little bit. They have to do weekly quizzes on the literature review that they read, as well as on the textbook content that they read.
For the report that you are mentioning in IEEE format and so on, that's one per semester, or there are multiple modules and they have to do one for each module?
One at the end of the quarter. We're on quarters. So they write one at the end of the 10-week quarter, but then every other week they're writing a lab memo for the labs. Oh, and the labs are obstacle avoidance, wall following, go to goal, with and without obstacle avoidance, hybrid control, which I also got from Maya's book, where they do wall following and then go to goal and then path planning. And then they do the localization and the mapping, topological and metric path planning.
Oh, I have to say, Carlotta, I now have to first say thank you very much. Second, we're doing a second edition of the book with much more content. Jeanette is helping. So I hope you go back to it. Pass it on.
Please, yes. Let me know when it's out. I'll take a look.
Thanks.
Hey, Carlotta, this is Marco. Thank you very much for a very inspiring talk. I teach at Stanford a class on hands-on robotics, so I really resonated with many of your lessons learned and also tips. I wanted to ask you if you could elaborate a little bit more on the role of simulators. Of course, simulators are becoming increasingly sophisticated. So I'm wondering, what are your thoughts in terms of either replacing hardware or complementing hardware with the simulator? What are the pros and cons? Of course, one pro will be that you may make your course much more accessible all over the world. Basically, you would reduce the cost almost to zero. But of course, you would also lose something. So I was wondering, what are your thoughts in this regard?
I think I've talked about my cons already with the hands-on, so I want to talk about some pros. I think one of the pros, I took a MOOC from Georgia Tech not too long ago by Magnus Egerstedt, I think is the proper way to say his name. And he used a MATLAB simulator. And I did that simulator as part of the MOOC, and I loved it. And I think one of the pros is I really push my students to do algorithmic software development. Luca, one thing I did not mention is my students for the pre-lab for the course are required to show me a software design plan. It can either be pseudocode, it can be a flow chart, it can be a state diagram. I teach them what all of those are, and I tell them sometimes one is better. It could be subsumption architecture. I don't really care, but before they start coding their pre-lab, and I do grade it, is to show me that you have a plan. So I think one of the benefits of a simulator is hopefully they've planned out their software and worked out the kinks, because the students who do trial and error programming, which means I'm just coding blindly into the dark until it works, as the class gets harder, their failures become so big that they almost can't finish the class. Whereas the students who are doing that systematic software development plan, I tell them everything builds on everything else. By the time we get to localization, your follow center should have been perfect from back when we did the wall following lab, right? But the students who kind of ad hoc the wall following lab, their robot can't make a map because it keeps running into the wall, right? Because they didn't do it right back then. But if you're making a software design plan where you're making these subsumption architecture layers, where you turn the wall following on or off, or the obstacle avoidance on or off, then you now have these layers that you build on, and your software just keeps building up every week. So that's another big thing I think a simulator would help with, is get them away from this ad hoc, praying over my code kind of coding, but make this algorithm, make it work in the software, then you can deal with the errors on the hardware next after you've shown it works on the simulator.
And to what extent do you plan to include a simulator in your classes? And if so, what type of simulators you have in mind?
Well, I'm an electrical engineer, so I'm only going to include a simulator if someone makes it for me, because I don't have that skill set. That's not my gifting. But, the other problem is that our robot is made of pieces. Like, I have an old robot that we put it together. So if someone made a simulator for me, they're not, this isn't an off-the-shelf robot. So it would probably, the simulator would have to be, I assume, designed to specifically work for my robot, unless somebody makes some kind of plug-and-play simulator. I'm a big fan of MATLAB because I also teach controls. And so we use MATLAB a lot in our circuits and controls courses. So if I was going to do a simulator, I would like it to be in MATLAB. The other reason I'd want it to be in MATLAB is because I know they have an Arduino library, which means it can then seamlessly be transported into what we could do on the robot.
Carlotta, thank you again for this amazing talk. So I have a question, kind of going back to kits. So as I was looking at, through your talk, I saw like what seemed to be like an amazing evolution of your kits. And, sometimes you have these students who come in and they're building their own thing. And I imagine that this is just growing into, a big repository of parts that could be a part of this kit. So I'd really love to hear your thoughts on, in your mind, what really goes into developing a good standardized kit, or what goes into your development of that? And are things like modularity in the components, the cost, and if you have components, like what really needs to be there to you? So obviously maybe motors if you need to move, Are there particular sensors for, I guess, a particular price range that you think are very important? Camera, what are your thoughts on that?
Well, yeah, like I said, I've been through about 5 robots. And actually some of the first ones I changed from was due to difficulty more than anything else. They were programmed in Atmel on a PIC. And that was great for the EE students, but it was a nightmare for the students from the other disciplines. The reason I transitioned to Arduino, so the robot we currently have used to have a different controller on it. I kept the robot because I love the robot because it's durable, because students will drop robots in the hallway, they'll leave them in the cafeteria and all kinds of things. But I changed over to Arduino because I know Arduino is big on the internet, right? Remember, I don't teach coding. So by changing over to Arduino, no matter what they ask me, I can say, Google it. I'm not teaching you that, Google it. So that's why I changed over to the microcontroller that I have, because you can't come and tell me it's too hard, because I can tell you that middle school kids do Arduino programming and you're a college student, but you can do whatever you need to do with it. So that's how I picked the controller. That's how I merged on that. The way that I merged on the robot was really dictated by the labs. I knew I was always going to start with reactive control, obstacle avoidance. So IR and sonar are always high on my priority list. I've lately been playing around with Pixie cameras because I want to trying to do some color tracking, like for localization. We're now in the world, kind of like the Yoda one you saw. It localizes not just on IR and sonar data, but on image signatures. Like blue, yellow, green means you're in this part of the world, or green, yellow, blue means something like that. So I think cameras are big, but I'm still trying to get the Pixie camera to cooperate enough with my robot to give it to the students as an assignment. Photoresistors. I didn't mention this, Luca, but I also do Bratenberg vehicles. I do the cycle. So we do fear, love, aggression, and explore Bratenberg vehicles. So the robots have photoresistors on them as well. That's always a good one for reactive control, where the students have to then figure out what behavior is this robot exhibiting. Stepper motors, I've gone back and forth. We currently have stepper motors with encoders. I've also used DC motors. The way I decide on that is we do PD control or PI control for wall following. And that's where I talk to them about feedback control. So the encoders help them to correct odometry error and to learn what it means to have robot error and how to adjust the robot for goal-to-goal behaviors and for wall following. So because we do those, encoders are really good to have on the robot as well. Freshmen, we've gone between Arduino, SparkFun Kits, and Elegoo. Freshmen touching as much stuff as possible. Servo motors, DC motors, IR, photoresistors, potentiometers. So for freshmen, every week they're doing a different project with different electronics, so that by the time they get to the robot project, they're really familiar with building on a breadboard, reading sensors, collecting and writing to data and things like that.
All right. Well, Carlotta, thank you very much. I would like to thank you again for a very inspiring, I would say also very useful and actionable talk. I would also like to thank our guest panelists, Maja and Sherry, for sharing their thoughts. This is the last talk of the quarter for Robotics Today. On behalf of the organizers, I would like to thank all of the participants for following us during the fall quarter. We'll be back next year. We're still working on the schedule, and we'll announce it soon, so please stay tuned. That said, I wish you happy holidays and see you next year.
Thank you.
Thank you.
All right, everyone, we're clear. Thank you.
Thank you very much, Carlotta. I was really taking notes. As I said, I'm teaching a hands-on course in robotics, and a lot of the tips you gave are extremely, extremely useful.
I'd love to hear more about your simulator. If I could get a simulator that I could then modify to work with my robot, I'd welcome it. I just don't want to build a simulator from the ground up.
Yeah, well, in my class, we use ROS plus Gazebo.
Mm-hmm.
And so we use, we also use a simulator that was developed by somebody else, basically.
Oh, okay.
Yeah. But yeah, no, I think you really gave a lot of, as I said, very actionable tips.
Yeah, thank you.
So also same here, the suggestion you gave about the undergraduate course. I've been teaching this course for I think 3 years now, and the conclusions are really the same about, the size of the teams for this to work well, like, the type of assignments. So was very useful to see that you got to to these conclusions, and they make sense for you. And thanks in general for the suggestions, to be honest.
Yeah. Freshmen, you have to be very clear about their roles. Otherwise, one person will be sitting there playing on their laptop instead of working.
Yeah.
So you have to be very clear. Are you taking notes this week? Are you writing the code this week? Or are you building the electronics this week? But if you tell them to just work, the slacker is not going to do anything. And I make them turn in a memo where they tell me how many hours they worked and what your role was on the team.
How do you do the grading, Carlotta? Because the grading that you are talking about in terms of coding and comments and naming for the variables and so on is very time consuming, right?
Everyone gets the same grade in my senior class because I assume they're mature enough. In my freshman class, they do peer evaluations at the end of the quarter. And if there's a consensus among the other members that you didn't do anything, I will drop your grade by half a letter point or whatever. And I'll email and tell you why. And I have had teams where a student disappears and don't do anything. And, they don't share the grade at that point. Because when I was a student, that made me mad. So, no coasting over here. If you're not doing the work, you don't get the grade.
Yeah, I found your comments on the team very interesting as well, because I had this actually also on my list, this question, because yes, it's true. Like some people always get kind of pigeonholed into a particular role.
Right.
And by enforcing this rotation, I never heard of this, but I thought it was a really great idea.
Yeah, absolutely. I got that from someone else where you make them rotate because, you also have the bossy bunny on the team that wants to do all the work and take over. No, you can't be the leader from beginning to end. You got to let go of the
okay. Yeah. All right. Thank you very much. I have to leave. I have office hours.
Thank you. All right. Bye, everyone.
So much.
Bye.
Jeanette, can I talk to you at office hours?
Sure.
Okay, great. Okay, bye.
Enjoy this, everyone.
Thank you, everyone.